I hope everyone's doing well. We are looking here at a question provided to me by a particular viewer. I am Mr. Ish and thank you for joining me for this video. With regards to this function, we're seeing we have to determine the extreme values, the inflection points and the concavities. Y equals minus 2x times x minus 1 times x minus 3 whole cube. How can we work with this? When you're looking at this, you're looking at a factored polynomial. The determination of your roots, which are your x-intercepts, are easy. You have x equals 0, x equals 1, x equals 3. When you put those values in the original equation, you'll have corresponding y values of 0. So we already know our roots. They're easily determined. We have 0, 0. We have 1, 0, and we have 3, 0. One thing done. Now we have to do a little trick. Our trick is we have to expand this factored polynomial into its unfactored form. If I were to open this up and expand it, I need to do it because it makes everything else easy. And what would that be? When I expand it, this is what I get. Y equals minus 2x to the power of 5 plus 20x to the power of 4 minus 72x cubed plus 108x squared minus 54x. You have to the power of 5. It's a Pentic polynomial. Now what we will do is the derivative of this to determine our critical points. By using the power rule, it's easy. Here at the top I would be doing the chain rule, the product rule. It would become tricky, but this is very easy to handle. I have here a first order derivative minus 10x to the 4 plus 80x cubed minus 216x squared plus 216x minus 54. I'll do a second order derivative because I need to classify those critical points. Do the power rule once more. Minus 40x cubed plus 240x squared minus 432x plus 216. That's what we have. Now what do we do? Keep in mind, I've converted this into a non-factored form. Then I do the derivative 1 and derivative number 2, and that's what we have. Look right over here and determine your critical points. How will you do that? You will convert this back into its factored form using your algebra. When you convert this first order derivative into your factored form, you have this minus 2x minus 3 whole square times 5x squared minus 10x plus 3. From here you're getting your critical point x values. You're getting x value from here, you get 2x values. You'll get here x equals 3. Here you'll get, using your quadratic formula, you will do minus b plus minus square root b square minus 4ac divided by 2a, and you get two values. Those two values, one will be 0.3675, 1.6324. You'll take these x values and you put them here in your original equation, then you get your critical point y values. You know one is going to be 3, 0. Your one root is also a critical point. When you put 0.3675 into your original equation, you'll get a corresponding y value. That will be minus 8.4811. When you put this right here, you have 1.6324. You put it into your original equation, you'll get your y value. That will be 5.2811. Now you have to classify these as either local minimums or local maximums. So there's a little bit of work over here. You convert the unfactored into the factored form, and from there you determine your critical point x values, and we've done that. Now we have to classify these. Look at these x values. You'll put them here into your second order derivative. When you put the 3 into your second order derivative, it zeroes out. It tells you that critical point is not a maximum or minimum. It's probably a saddle. Put this 0.3675. You're not looking for the exact value, but you're only looking, is it a positive or a minus? When you put 0.3675, what do you get? You'll have an output here. In this equation you're putting it in, you'll have a positive. Means you're looking here at a what? A local minimum, because you're going from negative tangent lines to a 0 to a positive. When you go from a minus to a 0 to a positive, you're looking here at a local minimum. It's a minimum, so you have a positive output. So we're looking here at local minimum. Now what happens when we put the other critical point, 1.6324? Well, when we do that, you put it into your second order derivative, you'll have here, you put it in, you'll have a negative output. That's telling you you're looking here at a local maximum. Why would that be the case? Because you're looking here from tangent lines which are positive to 0 to minus. You're going from a positive to a 0 to a minus. That tells you you're going over a hill, a crest. It's a local maximum. So we've determined that, and it's good. Now what we have to do is determine our inflection points. How can we do that? You look at your second order derivative. If you were to refactor this out using your algebra techniques, we can do it. We'll have minus 8 parentheses x minus 3 parentheses 5x squared minus 15x plus 9. From here you'll have 3 values. From here you'll have 1. From here you'll have 2 values. Here you're getting a 3. So I'm looking here at my inflection points, and I'm getting one going to be 3 comma 0, because you put this 3 into your original, you get your y value. From here you use your quadratic formula, you get two values, and I'll put those out for you. Your 1 is going to be 0.8291 x value using a quadratic formula, and your other x value from the quadratic formula will be 2.1708. Then you put these values into your original equation to get your corresponding y values, and I'll put them out for you. When you put 0.8291, you have a corresponding y value from your original equation. That's your y value of your inflection point. Your y value will be minus 2.898. That's 1. 0.8291 comma minus 2.898. When you put 2.7108, you have a corresponding y value which is going to be a positive 2.898. I've done this work here on the side, so I'm just posting the answers for you. We took our second order polynomial, factored it, and we're determining our x values. These are x values of inflection points. Put them in your original equation to get your y values, and those are your inflection points. Now we have to classify these in terms of concavities. How can we do that? You look at our inflection point values. I have a 0.82913 and I have a 2.170. Put those in order. I have a 0.8291, then I have here a 2.1708, then I have a 3. I have concavities either to the left and to the right of each of these, and I have to determine that. And how can we classify these concavities? You'll put everything into your second order derivative. Take a value toward the left of this, will be like a 0. If I put a 0 in here, I'm going to get an output which will be a positive, which means I'm looking at a concavity up. You're putting everything here into your second order derivative to classify your concavities. I take a value to the right of this, which is a 1. When I put 1 into the second order derivative polynomial, I have a negative output. I'm looking at a concavity down. Now look at this other inflection point x value, 2.1708. I'll take a x value of 2. I put it here and I'm looking at a sign. Is it positive or negative? When I put 2 over here, I have a negative output. It's a concavity down. I'll take a value now towards the right, which will be the same as a 3. So I can take one value here which will count in two purposes, and I can take like 2.5. When I put 2.5 into my second order derivative polynomial, I have an output which is positive and it's concavity up. Now I'll take a value towards the right of 3, and it can be like a 4. When I put 4 over here, I have an output which is a negative. I'm looking here at a concavity down. Now we have everything we need to graph our representation, and let's bring it out. I've erased everything and I'm going to put the graph right over here. Look at our roots, 0, 0, 1, 0, and 3, 0. Notice that root 3, 0, a critical point 3, 0, and inflection point 3, 0. 3, 0 will end up being a saddle point. Let's graph these out. 0, 0, 1, 0, 3, 0. Look at our critical points. This right there is not of any concern, but look, 0.3675 comma minus 8481 is a local minimum. It'll be somewhere right over here. Local maximum 1.6324 comma 5.2811. It'll be somewhere, if this is a 0, 1, it'll be somewhere right over here, not as high. I'm going to connect these and it'll look something like this. Come over here, and now it's going to be a saddle over here, and then it'll be like this. This right here is what I have. Now let's bring in our inflection points. I have a 3, 0, which is right here. That's one inflection point right here. We'll call it IP3, inflection point 3. We have a 0.8291 comma minus 2.898. If this right here is a 0, 0, this here is a 1, 0, and here's a 0.3675 inflection point, then 0.829 will be somewhere right here is my inflection point 1. Look right here, 2.1708 comma 2.898. This right here is a 1, 0. This right here is a 1.6324, my local maximum. Then 2.1708 will be somewhere close to 3. We can just say it right here. Here's my inflection point 2. Now we have our concavities. When I did not connect this too well over here. Let me redraw it over here. It's gonna go right here to the origin, as you know, because that's a root 0, 0. Let's map out our concavity intervals based on these values here, from minus infinity up to my this inflection point x value, which is what, 0.8291. I am looking over here at a concavity up. Then from this inflection point x value, which is 0.8291, to this inflection point x value, which is what is it going to be? 2.1708. 2.1708. I'm looking over here at a concavity down. Then from this inflection point x value to this inflection point x value, which is your saddle point, your root, how will we write that? 2.1708 to 3. I'm looking over here at a concavity up. And lastly, from this 3 comma 0 up to infinity, I have here a concavity down, and that's what it is. Minus infinity to 0.8291 concavity up, 0.8291 to 2.1708 a concavity down, 2.1708 to 3 your saddle point concavity up, and then 3 up to infinity your concavity down. We're done and everything is good. And we have everything mapped out for you. Your roots, your local minimum, your local maximum. Your root here, root here, root here. Your local or relative minimum, your local or relative maximum. Your inflection point, your inflection point, your inflection point. My original function, which you remember to be, is this: y is equal to minus 2x parentheses x minus 1 parentheses x minus 3 whole cube, and we're done. It's a Pentic equation and it's rather cumbersome to deal with, but we're good. My concavity intervals are right, inflection points are good, critical points, roots are good. This root, this critical point, and this inflection point will be your saddle point because it's serving many purposes. It's a critical point, it's a root, and it's a saddle. From a concavity up to a concavity down, you have a transition. That's it for this video. Thank you for watching.